Hello, everybody. Let's get started. This is the second talk from ARM today, and it's all about graphics, neural graphics. It's all about AI and the way in which we can all join forces and participate in what is a really exciting moment in history. Title, name, won't worry about the name. I work for ARM. I work with developers all around the world talking about technology, what's going to make a difference for them, performing research, developing products, providing tools. It's a great way to live, and it brings me towards people like you. Now, the title we're going to unpack. There's plenty to it. But we're here right now. We exist at a point in history at which we can readily acknowledge that AI is having profound impact everywhere. It's here in computer graphics. It's elsewhere in medical field. You can find it in automotive. Everywhere you look, you will find a domain in which one can apply AI techniques. And in the graphics field, I feel it's fair to say it's undisputed now. You can use, and many game developers do use, techniques in the PC console space to great effect. And inevitably, with technology, you will see a funnel effect. It will move from hardware to hardware to hardware. And since I'm standing in front of you as a person from ARM, you should anticipate that we want to present a mobile story, and that is absolutely to come. We want greater developer participation in this story, though, whether you happen to be working on a mobile form factor or something a little bit roomier. We feel that in the future, people will not only be able to benefit from models that have been trained by others, but they should be free to design, develop, train, polish, optimize, deploy their own models for the domains that they want to apply themselves to the ecosystems that they're delivering. And in order to do so, we need to make some changes. We need to make sure that we have everything provisioned in front of the world where we can all pitch it. We can all enjoy the benefits that are to be found. Now, I'm not going to pretend that this is a unique talk. You only have to go onto Google or take a look at the roster of talks that are here at SIGGRAPH this year. There are many neural graphics stories, many techniques around AI that can be applied to the graphics field. The way in which we position ourselves is that it's all going to be based on open standards. We want to make sure that people are included, that they can participate, and that we all have agency in this space. And I think that's going to be vital for the future. It's the thing that will drive innovation. It's the thing that will take us on forwards further and faster. Now, since I am speaking to you primarily about real-time graphics, this inevitably brings in graphics APIs. And there are many ways to implement AI in this world, but they're not open. They aren't ways that necessarily fit the mode in which you might want to work as a developer. And what we're proposing is that for neural graphics use cases, there is a very natural marriage between Vulkan, where we perform much of our graphics compute, and the ML workloads that we wish to apply to them. And therefore, we are proposing extensions, have proposed extensions, that we're seeking ratification from. We want to see this not simply as an ARM extension, but rather something that is more pervasive around the software development world. And that's something that is work in progress. However, if you're curious, you can absolutely look at the standards that we have got published. And you'll see that what we're trying to do is, first of all, deal with the basics. So what is a tensor? What is its rank? What is its shape? And furthermore, when we look at individual components of that tensor, well, exactly how are they defined? Which types are we talking about? So our proposal splits into different profiles, and the leading profile for us is quantized ints. And this is the baseline profile that we'll be working with in our ML extensions for Vulkan. Floating points are an additional profile. And of course, they're very relevant too. Now, my colleague Sam spoke earlier about the way in which we're addressing execution of AI workloads. And rather than it being sort of imperative operation by operation, this is a dispatch approach, which is to say whole workloads are executed at once in this model. You can, for most AI, you can imagine that a directed graph is something that is sufficient to describe the various combinations of operations that we're going to perform in execution. And so we have a format or a proposal that represents that. Now, in order to execute our workloads, operators must operate. I think that follows. And the way in which we're approaching this is as an extension of SPIR-V. And the extension is based around TOSA, the operating open standard for tensor operations that you can read up about. It's a relatively primitive set of operations that can be used to construct higher order kernels. And that's the way in which we're looking at this. From my point of view, again, this becomes a relatively natural way of thinking about how to implement, because a compute pipeline is a compute pipeline, a tensor pipeline is a tensor pipeline. Dispatch, sync, go ahead, all within the same programming model. Similarly, the operations inside of your workload are much the same as anything else that you might want to implement in SPIR-V. It all lives together. And that to me is a helpful thing. There are many possible innovations that you can look at within the neural graphics space, and what we're going to do is share a few examples. So we're offering neural supersampling as a use case that you can study, that you can train against, polish for your own content, but more importantly, any form of experimentation that gets you on that road. The key thing, and the thing that gives me a lot of pleasure, is when we think about this approach, you as developers are freed up to develop your own use cases, to offer your own innovation, and integrate those into your own software. But NSS is a place to fix your eyes. I think it's all fairly well understood in the literature what super resolution means. There are many great examples out there, both neural and classical. And so it's easy to wrap your head around if you're looking for practical examples. Our network is a kernel prediction network. It takes simple inputs, much like every other that you might care to see. So from the G buffer, we're going to take our colors, we're going to take our motion vectors, we're going to take our depths. And this is the way in which one works forward in order to produce the reconstructed upscaled image. In order to make this thing more real for you, we also produce educational content and samples that, again, we want to offer on an open basis. We want for you to be able to look at this material and decide for yourself, well, how does this match up? This then is a piece of content that we manufactured ourselves, and we will ultimately put out there for you to download and experiment with yourselves. It's developed in Unreal Engine by our content team. And as you'll see on the left-hand side of the screen, you've got native resolution there at 1080, and that's upscaled from 540. So 1/4 of the pixels rendered, and then upscaled by a factor of, well, let's say 2 in each dimension, or 4. I love looking at faces when reconstructing images, simply because as human beings, we're really, really good at recognizing mismatches. And so when we stare at a human face, we have that inbuilt instinct as to whether things are going right or wrong. There's a great gut feel about this, alongside simpler tests of moving geometry, which I think are vitally important also. Now, graphics is both an art and a science. We can offer these hard IQ measurements as to how our content performs, and you're very welcome to look at those. But I will acknowledge that intuition, gut feel is absolutely vital still into determining whether your graphics are just right. Nonetheless, you have a leading PC technique marked up in green. You have our technique that is intended to be both compact and suitable for deployment on mobile form factors in blue. And then you have our previous generation solution, ASR, in orange. ASR being a classical solution that has been derived from FSR2 by AMD, that we modified in order to make sure that it performs well within a mobile power envelope and time budget. A key feature here is that we are ×2 multiplication in each direction for green and blue, so as to say PC and NSS, but the scale factor, in order to maintain some reasonable semblance of quality, is only 1.5 in the case of ASR. And I think we can agree that although it tracks well in places, there's still a significant quality gap between the neural and the classical components here, which means that in mobile terms, well, you're not quite getting the quality bar, but you're also consuming more bandwidth and more compute in the process by which you upscale. So what we're then saying is, perhaps to no surprise, neural techniques are going to win here. Neural techniques are going to be extremely valuable, to us in the future and round about now. This is nothing without the developers. And to me, this is something that I think is super important. Through our openness, through our sharing, whatever we happen to say on a stage, you're in a position to experiment with and make your own decisions about. So I'll point you to some more of these key features. As I mentioned a moment ago, these networks are quite compact. The network for NSS stands at about 150K. Now, 150K, if you compare that to a typical, say, texture asset that you might ship in an application these days, that's pretty small stuff. Which means that you have all sorts of interesting possibilities here because models of this size become conceivable to ship as first-class assets in your applications. Models, mesh, textures, animations, AI. It all becomes open to you for development purposes, and I'm pretty excited about that. So for those that want to dive in and actually develop models, we're providing the support for that, which I'll mention a little bit later. For those who just want to cut to the chase and taste the effects of this particular use case, we're also supplying you with plugins for Unreal Engine, so you can try this out on your own content and see what the fit is, or indeed try it out on our content, this Enchanted Castle, as when we release that. So where are we showing up? We're showing up in places that we think make sense, that we think are helpful. So from the top down, we are providing game engine plugins for people who simply want to realize the benefits. We're providing a model for people who want to refine, train all the things that they want to do. And since at this moment in time, there is no mobile silicon that can run these techniques, we're providing a PC Vulkan layer that you can use in order to try this out on your desktops. As my colleague previously mentioned in his talk, this is bit accurate stuff. What you see is what you get. And so you'll be able to make rational decisions about the form and the future of technology like this. For those who want to go deeper, we've got the sample code, we've got documentation, we have various technical articles that will allow you to do just what it is that you feel is right within the context of neural graphics frameworks. And so in this first round of tools that we're releasing today, we can show you that you've got all of the things that you might regard as table stakes, the things that are essential for you to work with models, to debug models, and in fact to execute models on your desktop. For those, again, who just want the quick start experience, we've got the guides, we've got the plugins, we've got the content. Come and see. Now, we shouldn't imagine that that's the be-all and end-all. Just as we've seen in the PC space, there are other well-recognized use cases in real-time graphics. So frame rate upscaling and ray denoising are two more key use cases that we're working on. And our roadmap means that we'll be offering these on the same open terms as time moves on. So watch out for a continuing story there for models that you can evaluate and experiment with, because you'll be very, very welcome to it. People have made demos alongside us. One that we can speak of openly came from our friends at Sumo Digital. And if you happen to join us in meeting room 10 in the East building, you can see this demo live. You can get opinions from the folk at Sumo if you bump into them about the ease of deployment and development in this particular use case. It's positive. We want to make things simple. And also we want to hear from you about the way in which you'd like to do things. There are others. And I think to underline the point that I began with, we really do believe that the future for AI in this field and in others is an open one. We do need the standards to work around that we can all share in order to make this a practical reality across a great many devices, and to bring in the possibility of inclusivity and your own innovation, because this is the thing that is really going to accelerate us even further into the future. We have a number of partners that you'll see listed here who are gracious enough to join us in early access to date, and they have their hands on the tech, which is wonderful. You're very welcome to do so too. So you can visit our website to sign up for early access. You can come over to Hugging Face to see our model cards, dive into the GitHubs, meet us in our meeting room. Do all of those things if your heart and soul moves you. And I'll add a little extra special thanks to others that have collaborated with us. So Tencent Games, are great partners in terms of the feedback and deployment of solutions, as are NetEase. So with all of that said, I'd like to thank you all for your attention and hope that you are excited about the future of a more open AI in neural graphics.